There it is. Okay, share screen. Okay, so this is sort of a summary of the abstract broken down into bullet points. We're looking at series and parallel impedances in the quantum Hall effect. So the concept of impedance matching got lost in quantum mechanics. You don't find the near field interaction impedances in the curriculum, the textbooks, or the journals. And this is important because this is what governs amplitude and phase of energy transmission. So there's two possibilities for topological matching, which are either magnetic or electric coupling. For the scale-dependent geometric modes, you need both because Maxwell's equations operate in the causal scale-dependent modes, but in the topological modes, either one. It's just a phase shift. There's no amplitude. No work is done in topological interactions. So the measured quantum Hall impedance is what we see in the series configuration. It's the sum of the magnetic and electric couplings. But there's also the possibilities of a parallel configuration, which is down at about 5.5 ohms. And branching ratio calculations, you'll see a little bit later, they require this 5 ohm impedance to get the pi zero branching ratio at 2 parts in 1,000, and the eta and eta prime at 2 parts in 100. So this is of interest in condensed matter, obviously. We're looking at it for the vacuum in some sense. We're looking at vacuum impedance networks, but it's also curious that the forum, the electromechanical transducers turn out to be in the 4 to 8 ohm resistance impedance. And the fractional quantum Hall effect, this could be interesting in the fractional quantum Hall effect. So how it was lost in quantum mechanics? Bjorken summarized an analogy between Feynman diagrams and electrical circuits, with Feynman parameters playing the role of resistance. And Sun found this way into Bjorken and Drell, his textbook. And what thwarted him here was this topological impedance that we see. So the topological duality of electric and magnetic charge. This is a Physics Today article that was an interview of Witten. And in it, he described his best work. Oh, not there, but here in the CERN Courier article from December of 2021, he said this was his best work, was this duality, this electric and magnetic charge duality. So what happens if you substitute h bar over g for the electric charge in the formulas that define these fundamental lengths, which are separated by powers of the fine structure constant? It's inverted around the Compton wavelength because of the strength of magnetic charge. And this topological inversion, it shows up in our system of units, that the units of mechanical impedance are kilograms per second. You'd expect that means more flow, however, it means less flow. More impedance means less flow. So Feynman was looking at this, Bjorken was looking at it, and it's very confusing. It was backwards here. He thought it was resistance. The reality is his seconds per kilogram was conductance. So the intuitive advantage that he anticipated didn't materialize at that time. The mismatches are Feynman's regularization parameters of QED, and this makes QED finite. The model we're working here is finite without renormalization. So how it was found, you saw, let's look a little more at how it was lost here. The concept of exact impedance quantization didn't exist until the quantum Hall effect was discovered in 1980. And it was comparatively easy because it's scale invariant. The scale-dependent impedances, quantum scale-dependent impedances, it's a little bit harder to dig them out. And the other thing that happened was the theorists had a habit of setting the fundamental constants to dimensionless unity. And they included the impedance of free space in this, and so then they forgot about it. It just slipped over the horizon. How it was found, here we have a vibratory pile driver. We have a couple eccentric weights and they're counter-rotating, synchronized and counter-rotating in opposite directions. So they pull down, they oppose each other horizontally, they pull up, then they oppose each other horizontally again. So this is transforming 2D rotation to 1D translation. And it's an analog of the Clifford product. This is the dot product part of it that lowers dimensionality. The interaction of the Dirac equation electron and positron spinors counter-rotating in phase space. So it gives us a mechanical impedance, a way to calculate mechanical impedances. And mass is quantized in quantum mechanics. So right away, you've got a quantized electromagnetic impedance network. So that work, building, operating, and designing, building, and operating these pile drivers led to this paper on that was driven by Mach's principle, basically the principle of background independence, and it presented a strong epistemological argument, how we know what we know. The paper was submitted to the American Journal of Physics. Ed Taylor was very helpful. He was the editor at that time. It didn't get published. There were calculations for the hydrogen atom, deflection of light by gravitation, and escape velocity there. The referees said no ideas. It finally did get published as an appendix to the electron impedances paper. How to calculate, you can find at this link here. The links are active in the PowerPoint file, which I'll post on my author page on ResearchGate. Which is also here, the ResearchGate. Anyhow, what the timeline for the impedances, these are the classical impedances, the earlier experimenters, the Q meters to measure resonances and bridges to get more sensitivity, and then network analyzers. This was a big step here. The last network analyzer and the first digital network analyzer were both in the middle of the 1960s. That jump to digital was a big deal. The QED foundations were laid here, which was the model for quantum field theory. And the actual impedance, the concept of exact impedance quantization didn't show up here until here. So you needed this to get it into there to some extent. You had to know there was such a thing as exact impedance quantization. These are various theoretical efforts. In the yellow, with Jackson and Jovitz, Bajorkin, Feynman, and Vernon. Finally, here we have this 1975 paper on mechanical impedances. These are experimental results for the quantum Hall and fractional quantum Hall, and then again theory for the fractional quantum Hall Nobel. And now we're just sitting what I'm calling on the threshold here. We've got this idea of generalizing the concept of impedance to the scale-dependent impedances as well. And this happened in 2011, as you'll see on the following slide. The first step was the photon impedance match to a single free electron. So here you see a photon coming in from the right. The horizontal scale here is photon energy. So 0.511 ME photon, the wavelength is the Compton wavelength of the electron. And this is the mass gap in quantum electrodynamics. It's the lightest charged particle to couple to the photon, the Rosetta Stone, I guess you'd call it, of quantum electrodynamics, is that interaction. So as the photon approaches the Bohr radius of a hydrogen atom, the near field impedances of the hydrogen atom, the inductive impedance and the capacitive impedance, they shift the phases such that the inductive impedance advances the phase and the capacitive retards, and that decouples the two flux quanta of the photon. It breaks Maxwell's equations. So what you see then coming up to here is you get this impedance match from the 13.6 eV dissociation energy of hydrogen atom up to the quantum Hall impedance, which is also the centrifugal impedance. We need both the near field impedance of the photon and the near field impedance of the electron. That was a little bit over a year later before the electron impedances got sorted out. And after that, then another year to extending it to the unstable particle spectrum. So the electron impedances paper here, you can find there, the main point of this is we have this possibility of observing an additional quantum Hall impedance of a few ohms. So the way this works, if here we said at the electromagnetic radius, this is the Compton wavelength, the electron right here, and it's the same thing. This is the classical radius down here, which is also the electromagnetic radius. You got to compress that electric charge down to the classical radius before it has the energy of the electron itself, which is sitting out here. So that looks the same basically as this, except at the Rydberg now we're putting it at the Compton wavelength. And what we see here when we calculate the impedances, it's the same at either wavelength, is that we've got an electric impedance and a magnetic impedance, and with the topological inversion, you can see that the impedances are inverted as well. This is almost the quantum Hall impedance, and that's this much smaller 5 ohm impedance. And here alpha is the fine structure constant. So all we're doing is expanding in the power of alpha here and then scaling it to the impedance of free space excited by the photon, the 377 ohms. So their sum is the quantum Hall impedance. This was done in 2010, this work, and 2011, but the best value for the fine structure constant at that point was this. And with that, we had their sum is this value here, and out at 1, 2, 3, 4, 5, 6, 7, and 8 significant digits where we differ. So it's pretty accurately the sum. And the difference, again, is this parallel impedance down here at 5.5 ohms. So the theoretical minimum of the model we're working with, if you take a look here, the machine learning gives a nice overview of what's going on with this. But we start with just geometry, point, line, plane, and volume elements of Euclid, and then we say, okay, with the Clifford algebra, we start with the three-dimensional algebra for the vacuum wave function. It's a scalar, 3 vectors. The lines, 3 bivectors, and a trivector. You need the 3's here for the 3 orientational degrees of freedom. And this is the same at all scale in the geometric representation we're working here now, as opposed to the matrix representations that we usually work with. And the matrix representations are actually the basis vectors of space and space-time in the geometric representation. Then we have to quantize it. We have both geometric quantization and electromagnetic quantization via the coupling constant here. The 4 fundamental constants that define alpha, various combinations of them, permit assigning topologically and geometrically appropriate flux quanta to the 8 wave function components. Then you can multiply these things together, and what comes out is, and the interaction is via the geometric product, the sum of the dimension reducing dot product and dimension increasing wedge product. So if you start out with 3 dimensions and you multiply 2 3-dimensional wave functions together, the dimension increasing property increases it to 60 phase space. And time is the integral of phase. Each orientational degree of freedom requires its own phase, but time, you assume the evolution of time. Time is the integral of phase, and it emerges from the interactions. It compresses it, compacts it down to 4D Dirac algebra. There's a nice paper on naturalness here that discusses this sum. There's no free parameters in what you're looking at, so everything you see is just comes out of, in what follows comes out of these 3 assumptions. So you can generate a scattering matrix. If we start off with the electric charge and the magnetic moment, this is the Dirac spinner, and we say we're going to extend it now from the 2 spinners of the Dirac equation, the electron and the positron, to the full 8 components of the geometric representation. And it looks like this. So the things that are that have these colored symbols here, we can plot the impedances associated with those modes, and that's what we see here in this impedance network. The photon coming in, and as it gets to the Compton wavelength again, the phase shifts cause the flux quanta to decouple. It breaks Maxwell's equations. The correlation of the lifetimes, what we have here is the lifetimes, or you could say the coherence lengths, the lifetimes multiplied by the speed of light for the unstable particle spectrum. And these are spaced in powers of alpha, except here we've got a root alpha around the Compton wavelength, and it alternates between fermions and bosons. This is related to the weak interaction and the fact that neutrinos are present in all of these decays. Earlier I mentioned the pi 0, eta, and eta prime branching ratios. Here we need these impedances here, this impedance down here, as well as these up here, and perhaps another one down here, although it's not clear you need that one for this. And this is required for all three of these, the pi 0, the eta, and the eta prime branching ratios. And the calculations are accurate at the 0.2% level here and at the 2% level for here, for these two. So is there anything else we want to say here? Again, the Witten's paper on and how to calculate. So about the impedance model, its origin is in the S matrix bootstrap, and which is also the timeline of string theory. There's no Lagrangian. The equations of motion calculate the impedance networks, and so the bootstrap, they were foiled by a few things there. They really did need to know the phase shifts from the impedances. Part of it was they couldn't get the phases worked out, and another part was they were working at the wrong fundamental length. They were working at the nucleon wavelength, but you have to work at the mass gap. You have to work at the electron Compton wavelength to understand what's going on. So the model is gauge invariant. The impedance is what regulate the phases, and that replaces the covariant derivative in the model. It's finite without renormalization. Both the singularity and the boundary at infinity the mismatches are infinite. You can't couple to them. The confinement's the flip side of finiteness. The energy gets reflected back to the Compton scale by the mismatches. It's asymptotically free. The modes are matched at the nodes. The origins of mass are present in the model, as well as the equivalence principle. The gravitational mass comes from the impedance mismatch to the Planck length event horizon. That's the phase shift that the amount of energy that does not get reflected back from the Planck mass is the energy that's present at the Compton wavelength. And the inertial mass comes from the electromagnetic field energies of the wave function components. So it contains the four forces. It's got dark matter, dark energy. To summarize here, we talked about how impedance matching was lost, how impedance matching was found, the Mach's principle, which is where the model started in the timeline, the unstable particle spectrum, and the photon and electron impedances. We looked at a little more detail on the electron impedances and the mass gap of QED, series and parallel impedances, the three assumptions of the minimum. The minimally and maximally complete, it's actually 8 by 8 by 8 scattering matrix, because when you look at this here, what we've done is the degeneracy of these three modes here, these three vectors. We've removed the degeneracy by supplying the magnetic and electric flux quanta, and those two additional degrees of freedom for electric and magnetic fields raise the dimensionality from 8 to 10 of string theory, with time emerging from the interactions. But also, we need another dimension now. This thing's actually more like a Rubik's Cube, an eight-dimensional Rubik's Cube. It's 8 by 8 by 8. And you can argue that's the maximally complete scattering matrix. So there's many possibilities in the orientational degrees of freedom, and of course phase is a continuous variable, so there's many possibilities in mode coupling. The unstable particle spectrum correlates with the mass gap impedance network, and maybe there's something interesting we can say. No, it's not here, it'll be on another slide. And we looked at some properties of the impedance model in the previous slide there. So the conclusion, there's this question, is there a possibility to measure and exploit to use this 5.5 ohm parallel configuration? We see the 28512, but and then just throwing in a little bit more here, is this what I'm looking for? What was I looking for there? Oh, here it is, the standard model Higgs. So we're showing the Higgs. These four, the super heavies, the top, the Higgs, the Z, and the W, you've got, they comprise a minimally complete 2D Clifford algebra. I think, do we mention that here? No, we don't. Okay. But the point being that even though we show the Higgs here because it's part of this algebra, the reality is that the present experimental limit on at least some of the Higgs modes is out here somewhere in this range here, which interestingly enough is also the mass gap. So one could argue that the Higgs gives mass to all of this stuff, but then out here somewhere the origin of mass is not necessarily so directly. The Higgs is not perhaps not so directly part of the picture there. And is there anything more? Well, here, let's get back to this. When we look at the Planck length, the impedance mismatch to the Planck length, we have this bifurcation here. This is interesting. And this happens at 10 to the minus 32 seconds at the end of inflation in the more simple inflationary models. A primordial photon comes in and excites from this side of the figure instead of the way we normally have the photon exciting things from this side of from the low energy instead of the high energy side. So this impedance mismatch from here to here, that's the origin of the gravitational mass. Chirality arises because the photon, if you say it's just not a superposition, but rather just one of the two angular momentum states, and also the first thing it encounters is a fermion on the top. That's the heaviest particle here, the heaviest mode. Again, the vacuum wave function is the same at all scales, so the Planck particle looks like the electron, except it's at the Planck length in this model, and there's an event horizon sitting there. And so I guess what would be interesting here, we're at 1.4 TeV if we, the Rydberg, and so at the LHC, if we could take a look here and see what's going on, if we could understand how to make a trigger for the LHC to look for these Rydberg modes, that could be interesting. And finally, if we go the other way out to the observable universe, here we see the graviton. The mass gap is the Planck mass here, is the Compton here. Out here at 10 to the minus EV, we've got the energy equally shared between the electric and magnetic fields, and we've got this bifurcation again, this impedance mismatch, which could be why we don't see the 10 to the minus EV axion. We have to figure out how to impedance match to that to see it. Muon lifetime is here, neutron lifetime is here. You see that, so if we say that the inflation is driven by the electric field and then the rotation is driven by the magnetic field, we know that at the Compton wavelength to order alpha, the rest mass of the electron is due to the magnetic moment. It's not due to the electric charge. And but as the energy then, so here at basically the scale of the solar system, gravitation would be at its full strength. Earlier times, gravitation would be weaker. The model seems to suggest antimatter flies up. So if the CERN antimatter experiment, I'm still curiously waiting to see if when they're going to tell us the answer to that question. And the energy goes into the rotation gauge field. This could be dark energy. It's pushing things apart, and eventually out here the electric field, then it becomes repulsive again, just as at the beginning. So that, okay, a little bit on geometric, topological, and parametric impedances. Oh darn, it's 3 o'clock. I hope I'm not too late to upload this. The geometric impedances are the translation gauge fields. The motion is parallel to force. The topological impedances are the rotation gauge fields. Motion is perpendicular to the force. They can do no work. They're the channel of non-local entanglement. And then we've got these parametric impedances. We need a nonlinear process for wave function collapse, and we've got a couple of them. One of them is the fact that we're changing dimensionality with the geometric product, which is what models the interactions, and that's certainly a nonlinear thing. But also the scale-dependent impedances, as the energy tries to escape, the impedances are changing in the scale dependence. And so a familiar example of this for the electrical engineer, at least, is the variable capacitor, the varactor, which we use to move energy around in frequency domain to modulate things. The child pumping a swing at twice the resonant frequency, and the energy shows up at the swing frequency, or bosons pumping fermions. If we've got the spin 1/2 fermion here in blue, and then oscillating twice as fast to spin 1 boson, and we look at the sum of the fields, we get something that looks like this Mexican hat potential here as we're getting this parametric thing happening. If you flipped it by 180 degrees, it would look a little more like a Higgs potential. So I hope that I get to upload this, and I'm going to stop the share and stop. Thank you. Thank you for the opportunity. Thank you for looking. I'm going to stop recording.